Hello. I guess it is being recorded. Okay, perfect. Yeah, it is recorded. Okay, so welcome to the last chapter of this course, which is about the Cartesian coordinate system and more geometric stuff. So in this lecture, I'll try to cover 11.1 all the way through 11.4. Now, okay, so let's start with 11.1, which is 11.1 of Apex Calculus. So we are going to follow chapter 11 for, we're going to follow the Apex Calculus for chapter 11. Okay, anyway, let's start with it. So what is this chapter about? This is about introduction to Cartesian coordinate system. So the question is, what are we going to learn in this particular section? Well, what I'm going to do, I'm going to introduce you to the 3D coordinate system and how certain specific figures and specific structures look like in terms of equation in the 3D spaces. So as you know, the 3D space has an inherent coordinate structure, right? So this is x, y, z. And any point in a 3D space has three coordinate x, y, z. What is x? Well, to find out x, first of all, drop a perpendicular light from the point on the xy plane. So what you're going to do, you're going to find out precisely how far this point is from x-axis, how far this point is from y-axis, and how high this point is from the xy plane, right? So namely, this is x, this length is y, and this length is z. So if you want to visualize a Cartesian coordinate system or this three coordinate axis, just look at the corner of your room, right? If you look at the corner of your room, you can see like exactly this structure, right? There is like the floor of the room will look like this, right? And then the wall would go along this so-called z-axis, right? So these are the walls and this is the floor. So what is x-axis? What is xyz coordinate? Your x and y coordinate are how you are sitting. I mean, what is your position with respect to the floor, right? Like if you sit on the floor, then what is your distance from the corresponding walls, right? And then your z coordinate is how high are you sitting. That's it, right? Also, remember that distance between 2 points are given by this following formula. My bad, just a moment. Mm, right? In other words, so if you have like 2 points, This is x1, y1, z1. This is x2, y2, z2. Then the length of this line is this expression d, right? That is the so-called distance in the Euclidean space. Okay. Up next, let's try to see certain figures in the 3D space and let's try to understand that equation. Okay. So for example, suppose I draw a sphere. You can imagine a sphere very easily, right? I mean, just try to imagine a soccer ball, right? A perfect example of a sphere. My bad. So we have drawn a sphere whose center is at the origin. These are as usual x, y, and z axis, right? And the radius is 1, right? So this is called unit sphere. And what is the equation of unit sphere? The equation of unit sphere is x squared plus y squared plus z squared equals to 1. Okay. Meanwhile, let me try to explain what does this statement means that the equation of the sphere is something. It means that if you choose any point on the sphere, by the way, we are calling it a sphere, but it is actually a spherical shell or just the upper side of the sphere. So it is like it is an entirely hollow thing. So there is nothing inside. It's not a solid sphere. So a solid sphere would have equation x squared plus y squared plus z squared less than or equal to 1. But this is equal to 1, meaning we are just considering a hollow sphere. Just like when you talk about a circle in 2D plane, it is not a dense circle, right? It's rather a circular ring, right? X squared plus y squared equals to 1. It it is actually a circular ring, not exactly a circle. I mean, okay, we sometimes call it circle, but depends on your terminology. Anyway, so keep in mind that this sphere is hollow, and this is just the outside layer of the sphere. So we'll always call it a sphere. And if we try to describe the points inside the sphere, we'll call it solid sphere. Okay, anyway, so it means that if you choose any point on the sphere with coordinate it will satisfy a square plus b square plus c square equals to 1 and vice versa. Meaning that if you choose any 3 point, any 3 number ABC satisfying a square plus b square plus c square equals to 1, that point ABC will be on the sphere. For example, you can see 1, 0, 0 is on the sphere. Something even more horrible, something like maybe square root e, comma, square root of 1 minus e, comma 0 is also on the sphere, e being the exponential, right? Etc. Right? So make sure you understand what do I mean by equation of a sphere. So this is equation of unit sphere. Makes sense? And why unit? It is because the radius is 1. So what is the equation of a sphere having centered at a point ABC with radius r? The equation is the following. So this the center of unit sphere is 0, 0, 0. Radius is 1. So the equation of unit sphere is x minus 0 whole squared, y minus 0 whole squared, z minus 0 whole squared equals to radius squared, right? And the same thing I'm showing you here, but for equation for sphere with center at a general point ABC and radius r. Okay, sounds good. So this is all about sphere. Remember this in mind. Remember the equation forever. Okay. So I might give you something like this. X squared plus 2x plus 4y plus y squared plus 7 plus z squared. What is the center of this center and radius of the sphere with this equation? You have seen similar problems in previous lectures, but for circles. So essentially try to see that this thing is equal to x plus 1 whole squared. Sorry, 0. X plus 1 whole squared plus y plus 2 whole squared plus z squared equal to 0. So center, I shouldn't say 0. I should say maybe, I don't know, 4. So center is what? Center is -1, -2, 0, and radius square root of 4, right? Which is 2. Something like this. Okay, so keep this kind of questions in mind. Second, we want to discuss about planes. So what is a plane? We all know what a plane is. I mean, draw the coordinate axis first. And what is a plane? This is something like this. Oh my God, what has happened to GoodNotes? Right, and it is going in this direction as well, right? So I'm trying to why I'm drawing dotted, meaning that the ends are not yet met. They're like infinite structures. So planes, sorry, planes are 3D analog of lines, right? If you try to take a line from 2D space to a analogous structure in 3D space, that's going to be a plane. But remember, there are, lines and planes are two separate concept in 3D, right? I mean, you don't consider your pencil to be a plane, right? Your pencil is just a finite line. What is a plane? Try to think of, I don't know, maybe open ground. When you look when you look at open ground, just a moment. Yeah, so planes and lines are two different concepts in 3D plane. But yes, the analogous structure of um, plane lines in 2D you can think of as planes. What are the equation of a plane? Well, these are defined by inequalities, to be honest. For example, suppose look at this example in the textbook itself. Region defined by -1 less than or equal to y less than or equal to 2. Meaning that you are supposed to find out all those xyz whose y coordinate is between -1 and 2. X and z can be anything. So what does this look like? Yeah, it's kind of tricky to show, but I'll try. So say this is z, this is y, and this is x, right? So this is, so y coordinate is between -1 and 2. So this is -1. Okay, let me mark y, z, and this is x. So this is -1, this is -2. So y can vary between this two part, but x and z can be anything. So what that picture would look like. So essentially, it will be like two planes, right? So one plane will go through this. The other plane will go through this line. And then you have to, so this guy, this, this is one of the plane, and the other plane is this one. So this is like two planes. Okay. Try to look at the figure 11.1.1. So look at, because it is difficult to draw this thing on iPad. And keep using this app GeoGebra. But anyway, and why would be, and you have to like write, I mean, keep drawing these planes everywhere between this point 1 and 2. So this is not really two planes, they're like infinitely many planes, right? But bounded by this two region. Think of like stacked papers. So the stack length being 3 or something. Yeah, so these are like infinitely many planes, not two planes. Okay. But anyway, let me give you a very easy example of plane. For example, one more example of plane. Just consider this equation, z equals to 2. What figure does it depict? So draw the coordinate axis first. So you're looking at all those x, y, z, all those points x, y, z, whose z is 2, right? And x and y can be anything. So what is that? This is simply This is nothing but something looking like this right now. So this height is 2, right? And now extend this guy to everywhere, right? This is the definition of plane, or this is a picture of a plane, not definition. So and so on. Okay. So think of the xy plane, but elevated at the height of 2. So that is why we call it xy plane. So for example, the plane z equals to 0 is called xy plane, right? Literally, if you look at your room, your floor is the xy plane. The floor of your room is xy plane, right? The two walls are xz plane, depending on which side you are calling x-axis, and yz plane. This is the most neat example of plane. But anyway, your floor is a finite place, right? Try to imagine your floor to be everywhere, like an infinite floor. That's much better description of xz plane. Something like heaven in, all these heavens in Harry Potter and things like that. It's a infinite white space with an infinite white floor. That infinite white floor is your xy plane, and the infinite walls are like yz plane, and infinite walls are like yz plane, xz plane, things like that. So these are plane. Now see, you're standing on the floor, but imagine your floor to be lifted to 2 unit height. That would be like z equals to 2, which I was trying to draw here. Now try to tilt your floor and lift it. That is precisely what a plane looks like. So what is a plane? Take the floor of your room, lift it to some certain height and tilt it. That's exactly what a plane looks like. Okay. Any question? Okay. Then the next diagram is of that of cylinder. What is the equation of a cylinder? It is, okay, by the way, what is a cylinder first? So again, this is also an infinite structure, but I'm just drawing a finite part of it. Okay. Now try to lift it. Okay. Look at the textbook picture. Okay. So what is a cylinder? You can copy paste the definition. So as you can see, the cylinder always has a circular plane, right? So this circle has certain equation, right? The radius of this circle is called the radius of this um, cylinder. Okay. Okay. But for example, this is the cylinder created by x square plus y square equals to r square, right? So like if you look at the xy plane, there is a avatar of this plane living on the xy plane as well, right? So this is the x square plus y square equals to r square, but z equals to 0. This is x square plus y square equals to r square, but maybe z equals to z0 or z equals to 2. Okay, so try to imagine it in this way. Look at your floor, look at the origin. So the origin would be that corner of your room, as always. So look at the corner of your room. Try to imagine a circle on the floor that is centered in the corner. Okay. So definitely you cannot see this entire circle because there will be part of the circle outside of the wall. You will see only a corner or a quarter of a circle, right? Anyway, but try to imagine it no matter what. So look at the corner. The corner is the center, and try to imagine a circle centered at the corner of your room. Now try to imagine an infinite copy of that circle at every height of your room, starting from that corner. So, in other words, this is the corner of your room. This is the circle that you are trying to imagine. You are seeing only this part, right? But nevertheless, imagine it. Now try to imagine that circle on every height, right? What you will get is a cylindrical, infinite cylindrical shell. So what this part of text is trying to do, it is trying to do the same construction but for an arbitrary curve. So in this case, the curve, so this is the curve C, right? So instead of imagining a circle on your floor, you can imagine any 2D figure on the floor, right? You can imagine any 2D shape on the floor and still keep like putting it throughout the entire height of your room, right? And you will still get a structure. For example, try to imagine a parabola in your room, right? So this is y, this is negative x-axis, this is positive x-axis, this is z, right? So what does a parabola look like? A parabola on your xy plane would look something like this, right? Try to imagine this on your floor, starting from the origin. Try to imagine a parabola. So you can see only this part. You won't be able to see this part. This will be on the other side of the floor, right? Other side of the wall, not floor. Anyway, so try to imagine this parabola lying on your floor, and then again lift this parabola everywhere on the every height, right? Let me use a different color. So this is the parabola at height, I don't know. So this thing is y square y equals to x square, z equals to 0. This is y equals to x square, maybe z equals to 5. Who knows? And then again, one more at a even higher, even in a bigger height, right? And try to keep drawing these parabolas on every height, on every point of height. What you will get, what you will get is something like this, a parabolic shell, if you want to call it like that. Right? Right? So this would be, so this is one of the walls. And then the other side of the wall would be like this. This is the other side of the wall. Right? So that is how this would look like. Okay. So how do you like visualize this? So look at the two walls. So sit facing your corner of the room. If you sit facing your corner of the room, you will look at the so-called z-axis, right? So try to look at the z-axis, try to look at the wall. Now try to curve the wall outside. So these are the walls, right? So you are sitting somewhere here. You're looking at the walls, right? And try to carve the wall outside. So that's what this diagram would look like. Okay. Have you seen, if you had seen Matrix, you know, there is a scene where like Neo is being shot, but now he's the one. So he's like trying to flex his body, but then the wall outside are also kind of getting thrown out way, right? So that's what this diagram would look like. Precisely that. So so there is nothing between here. I'm trying to draw the wall of this line and the wall of this line. That's it. And you are sitting between these two walls. So this is you. Okay. Try to visualize it. Okay, then we have to talk about the circle of revolution. So I'm directly copying it from the textbook. So what is surface of revolution? Well, you have a function on the xy plane, okay? Revolve it around x-axis. So you are getting a 3D picture. You have seen this problem many months before. What is the equation of that surface? The equation of the surface is, for example, say you are revolving y equals to square root x. what is the equation of the surface, right? So the surface equation is y square plus z square equals to the function square, right? Now instead of, I don't know, instead of a function on xy plane, you might have a function on xz plane, or you might have a function on yz plane, right? So even then the similar formula holds, but x would be y and y would be z. That's the point. So say that you are trying to revolve a function y equals to rx around x-axis, then this is the equation. If you are revolving around y-axis, then this is the equation. And if you are revolving around z-axis, this is the equation. An example. So say revolve um, I don't know, y equals to sine z for z belonging to the segment 0 to pi. What would be the equation? Around z-axis. Since you are revolving around z-axis, the equation is going to be x square plus y square equals to rz square, which is sine square c. That's it. Look at the textbook for this. Also, there is one more thing I should mention about revolution, which is this guy. So yeah. So previously, if the function is in x, you should revolve around x, right? But if the function is in x, but you are revolving around the other coordinate, what is going to happen? This is the formula, right? So for example, let me give you an example. So z equals to sine x, revolve around x-axis, then the formula is very easy, which we just saw. The equation becomes y square plus z square equals to sine square x, right? But instead, if we revolve around z-axis, remember the function is in x, but we are revolving around z-axis, then the equation is z equals to f of square root x square plus y square. So here f is sine x, so sine of square root x square plus y square. That's it. Okay. Finally, to conclude chapter 11.1, I'm just giving you the definition of the quadric surface. So what is quadric surface? It's the surface depicted by a general degree 2 polynomial in variable xyz, which I am going to show you right now. Homogeneous polynomial. Actually, not homogeneous. We don't need homogeneous. This is. So this expression that you are seeing, this is the general expression of a degree 2 polynomial in the variable x, y, z. So for different values of a, b, c, d, e, f, g, h, I, j, you will get different kind of paraboloid, hyperboloid, elliptic cone, ellipsoid, and things like that. For example, remember, a degree 2 polynomial in x and y gives you all the conic sections. For example, circle is x square plus y square equals to r square. Hyperbola, x square minus by square equals to z square. Ellipse, ax square plus by square equals c square. Things like this, right? So degree 2 polynomial in x and y gives you conics. 3D version of conics are called quadric surface. Okay. So for this, uh, yeah. So there are 6 basic types of quadric surface, right? So this is point number 1. Which are also described. So what is the elliptic paraboloid? Actually, instead of writing it down, let me just show it. Actually, I can write it down. Never mind. So elliptic paraboloid has this following equation. Then elliptic cone has this equation. So the difference is between z and z squared. That's it. What about ellipsoid? This is for ellipsoid. This is for one sheet hyperbola. Finally, hyperbola of two sheet and hyperbolic paraboloid. And since your exams are going to be online, I will give you equation and try to ask you question and identify the corresponding 3D figures. I have realized that the exams have been way too easy for obvious reasons. So these are the 6 types of quadric surface that you will see, and your fundamental work will be to identify these quadric surfaces.